Welcome to This Explainer. Today, we're diving into something absolutely crucial for anyone working with dynamic control systems, the incredible visual and mathematical elegance of polar plots. If you've ever wondered how engineers actually tame the wild, complex machines that run our modern world, well, you are in exactly the right place.
But before we get into the heavy math, I want you to think about a highly practical question. How does an engineer actually know for sure that a complex aircraft autopilot, or say a high-speed industrial robotic arm, isn't going to just violently spin out of control the exact second it's turned on? Solving massive differential equations for every single possible operating condition? Yeah, that's incredibly tedious and honestly sometimes impossible. We need a shortcut. We need a visual fingerprint of the system's behavior.
Here is our roadmap for today. We'll be decoding frequency response, breaking down the anatomy of polar plots, exploring system types and shapes, checking out stability via the Nyquist criterion, and finally, looking at some real-world applications.
Let's jump straight into part 1, decoding frequency response.
Think of frequency response kind of like this. When we feed a continuous oscillating sine wave into a dynamic system, we want to measure exactly what comes out the other side. The system is naturally going to change the wave's amplitude, meaning how tall it is, and its phase, meaning how much it's delayed. By sweeping through a wide range of frequencies, we get a crystal clear picture of the system's dynamic, steady-state behavior, entirely skipping the need to solve those massive differential equations in the time domain.
When we get down to the math, we do this by taking our system's transfer function and just swapping out the complex variable s for j omega. We can then represent this response in two ways, either as a complex number with real and imaginary parts, your r and x, or, and this is way more intuitive for what we're doing, as a magnitude and a phase angle. It's the exact same information, just a completely different coordinate system.
All right, part 2, anatomy of polar plots.
Here's the really cool part. A polar plot is essentially a single, continuous, sweeping curve. It's drawn by the tip of a vector right there on the complex plane as we crank the frequency, omega, from 0 all the way up to infinity. The length of that vector, that's your magnitude, and the angle it makes with the positive real axis, that's your phase.
Now, you might be wondering about Bode plots. Bode plots are fantastic, for sure, especially for pinpointing exact frequencies on two separate logarithmic charts. But the polar plot, it brilliantly illustrates the entire system behavior over all frequencies in just one single elegant curve. You might sacrifice reading the exact frequency at a glance, but you gain this holistic, immediate view of your system's stability margin. It's a real game changer.
If you're a student prepping for gate exams or an engineer designing controllers in a lab, these steps are your absolute bread and butter for sketching these vectors manually. You always start at 0 frequency, you find your infinite frequency endpoint, and then you calculate exactly where your curve slices through the real and imaginary axes. Those give you the solid anchor points for your sketch.
Visualize this in your head right now. As the frequency sweeps upward, imagine a vector anchored right at the origin. As that frequency increases, this vector rotates, usually clockwise, and actually changes length, tracing out this completely unique trajectory. That trajectory is quite literally a fingerprint of your physical system's behavior.
Moving on to part 3, system types and shapes.
This is where it gets really visual. Notice how the type of a system, which simply means how many poles are sitting right at the origin of the S-plane, dictates exactly where our sweeping vector begins its journey at 0 frequency. A type 0 system, it starts flat on the positive real axis at 0 degrees. If you add an integrator to make it type 1, boom, it starts pointing straight down at negative 90 degrees. Make it type 2, and it starts at negative 180 degrees. But notice, as frequency hits infinity, they all spiral right back into the origin.
Think about a physical spring mass damper, which is a classic second-order system. The curve's shape actually balloons out or pulls tight depending on its damping ratio, or zeta. And even more fascinating, the exact point where that sweeping curve crosses the imaginary axis represents the system's natural, undamped frequency, omega n. The physical physics of the machine are completely baked into the math's geometry.
So, what happens when we start messing with the system? Well, every time you add a pole to the system's equation, which mathematically adds lag to your physical system, it forces the polar plot to rotate further clockwise. On the flip side, adding a 0, which mathematically anticipates the signal, pulls the plot back counterclockwise. Engineering a control system is basically the art of adding poles and zeros to bend this curve exactly where you want it.
Let's hit part 4, stability via the Nyquist criterion.
To really grasp Nyquist, imagine a massive boundary enclosing the entire right half of the complex plane.
We care about this because that is the danger zone where unstable poles live. We take this giant contour, map it directly through our open-loop transfer function, and the result is essentially a complete, closed-loop version of our polar plot.
That massive mapping spits out a beautifully simple equation, z equals p minus n. It tells us that the number of unstable closed-loop poles, z, equals the number of unstable open-loop poles, p, minus the counterclockwise encirclements, n. If z ends up being anything greater than 0, there's no way around it. Your physical machine is going to go out of control.
And here is the absolute kicker, the magic point. Out of the entire infinite complex plane, the stability of our physical machine relies entirely on whether our polar curve wraps around the exact coordinate of -1 on the real axis. Why -1? Because mathematically, that is the exact threshold where the system's feedback loop shifts from correcting errors to dangerously compounding them.
Finally, Part 5, Real-World Engineering Applications.
Why does all this matter? Whether you are designing the speed controller for the latest electric vehicle, programming the incredibly precise movements of an industrial robot, or ensuring a commercial aircraft's autopilot can handle severe turbulence without oscillating, these polar mappings literally prevent your physical machines from breaking apart. As engineers, you are shaping invisible mathematical curves to guarantee highly visible real-world safety.
There's a quote from our source material that really hits the nail on the head. It says, "An advantage in using a polar plot is that it depicts the frequency response characteristics of a system over the entire frequency range in a single plot. Instead of flipping through dense pages of equations or cross-referencing multiple charts, you condense an infinite range of frequencies into one readable fingerprint. It's visual intuition completely backed by rigorous mathematics."
So, I'll leave you with this thought to chew on. If simply manipulating a geometric vector on a complex plane can guarantee that a massive drone stays stable in the sky, what other invisible mathematical laws are out there just waiting for you to master them? Thanks for exploring the elegance of polar plots with me in this explainer, and keep looking for the hidden structure behind the complex systems all around us.